Before we get started, please make sure that you have printed out the PowerPoint slides so that you can take notes as we go through the examples in this section. Also, I'm going to break this section up into two parts. So this is going to be part 1. And then I will post the second portion of this about halfway through the PowerPoint. So what we're looking at in this section is we're going to talk about inverses. And if we first start looking at a function as what we do to the original value. For example, in our function f of x here, we take x, multiply by 3, and then add 4. How can we undo that process? Well, we would have to backtrack. First thing, we'd have to subtract off the 4, and then we would have to divide by 3 to get back to the original x. And so as we work through all of our examples, we are trying to undo what the original function is telling us to figure out the inverse. And our goal for both of these is to get back to plain x. The original function does something, the inverse is going to undo it. So how do we verify that we have inverses? Well, we're going to use our function composition from the last section. So if we use our function composition, we can take g of f of x, and we would get that plain x. Likewise, we could take f of g of x, and we would get the plain x. If we get nothing but x both ways, then we have inverses. And the original function f is invertible. The function g is invertible. To indicate that we have an inverse, we use some notation rather than talking about the functions f of x and g of x. It shows up nicer on your PowerPoint than it does on this slide here, but we would have f with the little -1 of x, and that's our symbol to say that we have an inverse. There is only one possible inverse for the original function f, and our inverse is going to be reflected across that line y equals x. That was our function g of x on the previous slide. Now we come to some of the more interesting or a little bit tougher. So when we were trying to come up with the definition of a function, we said that for every input there was exactly one output. When we're talking about having an inverse, we have different inputs with different outputs. That's saying we have a one-to-one function. And we're going to talk about this f of c equals f of d, c equals d. This is going to be our analytic check, and I'm going to show you how to do this when we get to some of the examples. But if you look at my graph down here, you can see that all of my x values over here, these would be my x's, are mapping to one y value. That is a one-to-one function, compared to the other set where I've got some x values that are going to multiple, they're going to the same y value. And so this is not a one-to-one function. What does this look like if we were to graph it? I'll show you in a second. Again, when we were checking to see if we had a function, so like here's the graph of a function, is this a function? The answer is yes, it passes the vertical line test. On the other hand, I could make a graph over here. This flunks the vertical line test because it hits in 2 or more places. But this was to check if we had a function. Now our question is, do we have an inverse? So we have a different test. This test is our function 1 to 1. And we're using the horizontal line test. So if we draw a horizontal line test here, if we draw a horizontal line, clearly it's flunking. It's hitting in 2 spots. And this means we have no inverse. If it flunks the horizontal line test, I cannot come up with an inverse for this original function. Yes, it's a function, but it's not invertible. If I want to check to see, can I find an inverse, I need to see any of the following. First one is, yes, it's invertible. The other one is, it's 1 to 1 that I can prove analytically. That's using the C equals D check, and I will show you some of those. Or graphically, I would check out the horizontal line test. And so we will look at some of those examples coming up. So here are 3 different examples, and I want to check first by using the C equals D test, and then graphically I'll do that on the next slide. So in this first function here, to check with the C equals D, I am literally replacing 1 minus 2C over 5 equals 1 minus 2D equals 5. And my goal is to do this work to see if I can get C equals D. So first things first, I'm doing my algebra to solve this equation. I'm going to multiply both sides by 5 because who wants to work with fractions? So those are now gone. Now I have 1 minus 2C equals 1 minus 2D. I'm going to bring that up over here. If I subtract 1 from both sides, they're gone. So I have negative 2C equals negative 2D. And I think you can see that if I divide by negative 2, I have C equals D. This is my analytic check to verify that we have a 1-to-1 function. So this f of x has an inverse. Now you probably already knew that linear equations, you can find an inverse for them without too much difficulty, but this is the algebra that goes behind it. If I take a look at g of x, I'm going to use the same procedure with plugging in c's and d's, and this might get a little more complicated. 2c over 1 minus c equals 2d over 1 minus d. And actually, that kind of sets up something I could cross multiply maybe. 2c times 1 minus d equals 2d times 1 minus c. So let's multiply that out. And if I now look at my equation here, I have 2cd and I have 2dc, which is pretty much the same thing by the commutative property of multiplication. So those can cancel on both sides, and now I have 2c equals 2d. Well, that's great news, because if I divide by 2, I have just verified that c equals d. So g of x is also invertible. h of x is a parabola, and the last parabola we looked at was not invertible. So let's see what happens here if I try to plug in c's and d's every place I have an x. I would have c squared minus 2c plus 4 equals d squared minus 2d plus 4. Well, the 4's I can cancel because they're on both sides. And now if I bring over c squared minus 2c minus d squared minus 2d equals 0, I have 4 terms here that I'm trying to, it's a quadratic, I'm trying to solve for 0, and the first thing I would try if I have 4 terms is to factor by grouping. So I'm going to do a little rearranging. I'm going to get the c's and d's together, the c squared and the d squared together, and then the 2c and the 2d together. So then I'd have plus negative 2c minus 2d. Alright, so if I try to group these and try to group these, well, I recognize that I don't really have a common factor yet, but I see that c squared minus d squared is the difference of squares. So c plus d times c minus d. Oh, now I'm starting to see something that might work. If I pull out a negative 2, I would have c plus d. So c plus d comes out, and then I'm left behind with c minus d minus 2. Okay, so I would have c plus d equals 0. So that's saying that c equals negative d, not quite what we wanted. And c equals d plus 2, also not quite what we wanted. So I have 2 different options here as to what c equals, and that's a problem. I do not have one output for c. I have 2. This is not 1-to-1. This is not invertible. And if we take a look at our horizontal line tests for these 3 different graphs, the linear equation passes the horizontal line test with no problem. The other one, that happened to be a rational function, also passes the horizontal line test with no problem, but our parabola is failing the horizontal line test. And so graphically, it's also demonstrating why we have no inverse on that parabola.